Hi, okay, so welcome to the last part of our ionic equilibrium chapter. This one we're going to move away from acid-base chemistry and we're going to look at ionic solids and also transcription metals and the complexes that these transcription metals can form in water as well as with other ions. So today we're going to look at equilibrium for ionic solubility. We're going to introduce another K. So remember, K is your equilibrium constant, but now it's going to be K as it relates to ionic compound solubility. So that's a KSP. Some of the things that can affect that are called common ion effects. These are also very susceptible to pH and temperature changes, so we'll talk about that. Selective precipitation, equilibrium for the formation of complex ions, and then calculations involving both KSP and KF. And KF is something that we use when we look at these complex ion formations. So the F here is going to be for formation. All right, before we start this, it might be helpful to kind of backtrack a little bit because we are going to be talking about ionic compounds and ionic solubility, is to review those ionic solubility rules that you probably learned in Gen Chem 1. So I'm just going to review those really quickly here with you. And these are going to be our solubility rules. The first thing is I'm going to tell you that these are not hard and fast rules. These are actually guidelines because all ionic compounds can have some solubility in water. What these solubility guidelines are which ones are really soluble in water. Our first guideline is that all nitrates, acetates, group 1A metals, ammonia, that's one of your positive polyatomic ions, these are all going to be soluble. So it doesn't matter, it's going to be regardless of what the other ion is with it. And I'm going to add one more to that, and I'm going to say perchlorates. Perchlorates are also going to be soluble. So that's our first guideline. So in this one I have chlorine, bromine, and iodine. Those are going to be soluble except with the following metals, except with silver, lead, and mercury. Then these are going to be insoluble. So all sulfates are soluble except with the same three offenders, silver, lead, mercury, but I'm also going to add in calcium, strontium, and barium. These are going to be insoluble. So all your hydroxides and your sulfides are going to be insoluble, except with your group 1A metals and ammonia, and that kind of goes back to our first rule up here. Calcium, strontium, and barium, these are the ones that were insoluble with sulfate, but if I have calcium hydroxide, calcium sulfide, strontium hydroxide, barium, these are going to be soluble. They're not going to be incredibly soluble, but you're going to see some solubility there. So these were our solubility guidelines coming out of Gen Chem 1. So we're going to expand on that and we're going to say now I have the ability to look at solubility of compounds that I even before thought were insoluble. So is there any ions, if I have silver chloride in solution in water, are there any free ions in that solution or is it all just completely solid? What about something like magnesium hydroxide? So according to this, magnesium hydroxide would be insoluble because it's not on my solubility list over here. So if I had that in water, is it going to form any of these ions here? Will it dissociate into ions in water? And you'll notice that I'm using this here. This means that I have an equilibrium scenario. I might have a little bit that dissolve into ions. I could look at that in terms of an equilibrium standpoint, but now I'm going to have SP here. And this SP is specific for ionic compounds and it denotes solubility product. And it's going to tell me how soluble this is. How soluble is magnesium hydroxide? If I go by my hard and fast rules here that I learned in Gen Chem 1, I would say it's not soluble, but now we're in Gen Chem 2, we're going to move past these very finite lines and we're going to look at like really what's happening. So my KSP for this, if I look that value up, it's 2.06 times 10 to the minus 13. So I have a KSP value. I have a KSP, which means this is happening in water. There is some amount of magnesium ions, there's some amount of hydroxide ions that are being formed if I have solid magnesium hydroxide in solution. You'll notice the magnitude here of my equilibrium constant is really small. So minus 13. That tells me that the majority of the equilibrium in this scenario is lying in on this side, on the right side, with my unsolvated ionic compound, but there is a small amount of magnesium ions and hydroxide ions that are going to be in solution. So I can write my law of mass action for this. And remember a couple of things. These are solid, so that means that they're not going to factor in to our law of mass action. So remember, our law of mass action is only aqueous and gas, so this doesn't go into here, and my stoichiometry is important. So just like we've been doing in the last two chapters, we're applying it now into an ionic, the solvation of an ionic compound. That's what this KSP is telling me. I'm going to introduce, instead of solving for X, because these become ice tables because it's an equilibrium scenario, instead of solving for X, we have a unique way of looking at the number of ions that are in solution. And we're going to call that, instead of solving for X in our ice tables, we're going to solve for S. And S is this molar solubility of an ionic compound. It has units of moles per liter. So it's molarity, but it's molarity that's going to take into account the stoichiometry of your ionic compound. If I have an ionic compound, it depends upon the chemical formula of the ionic compound, how many ions I'm going to have in solution. And so S is going to allow us to sort of relate the solubility of an ionic compound, relate it to the stoichiometry of the number of ions that are in that compound. And we're going to solve exactly like we would be solving for X, but we're going to call it S. And then it's going to be clear in a little bit why we need to look at S specifically. All right, so this is called the molar solubility. And S is different from KSP. KSP is my constant, and this is going to be the molar solubility for each of these ions in solution. So let's say I want to calculate S for magnesium hydroxide. What I know is I have my KSP for magnesium hydroxide. I also have my law of mass action, so I'm going to set this up like an ice table. So my ice table, I'm going to not worry about my initial concentrations here because this is a solid. It's not in my law of mass action, so I don't really care what's happening over here. So my ice table is going to start here with my products, with these dissociated ions. So I'm going to assume that I start with 0 amounts of those. And then I'm going to have some change. This is going to go up by S. This is going to go up by 2S. So I'm just substituting S in here instead of X. So then this becomes S and this becomes 2S here. Now I'm going to plug this into my KSP. So this is my molar solubility for magnesium hydroxide. And one thing before we move forward in this chapter is I want to talk about the things that can affect the solubility of an ionic compound. So remember, KSP is going to give me the extent of solubility. S is going to give me my molar solubility, and this is going to account for various number of ions. And then things that can affect the overall solubility. One of them is going to be temperature, and the other one is pH. A lot of ionic compounds are very sensitive to pH, and so pH can either increase the solubility of a compound or it can decrease the solubility of a compound. Temperature can either increase the solubility or decrease the solubility, and temperature is going to depend if I have an endo or an exothermic solubility. If it's endothermic and I heat it up, then that's going to increase the solubility. If it's exothermic and I heat it up, that's going to decrease the solubility. So temperature is going to depend. pH is going to depend upon the composition, the ions that make up the ionic compound, and that's going to determine its effect. So we'll look at pH. Let's go back to magnesium hydroxide. What happens if I change the pH of this solution? So let's say I have adding magnesium hydroxide to a solution that has a high pH. That means there's hydroxide ions present in my water. It's very high. So what that's going to do is if I have a high pH, or I do something where I increase the pH of my solution, that's going to affect the equilibrium here, because if I have a high pH, that means I have a significant amount of hydroxide ions in solution. That's going to shift this reaction back to my insoluble reactant here. So if I have a high pH and I have a hydroxide compound, that's going to decrease my solubility because it's going to drive that reaction in reverse to the solid magnesium hydroxide. What if I have a low pH? That means I have hydronium ions present. And hydronium ions present are going to react with the hydroxide ions here, and that's going to form water. And so basically, if I have a low pH, these hydronium ions are being neutralized by the hydroxide. The small amount of hydroxides that are being formed as this dissociates, that forms water. That's essentially removing the hydroxides. So every time one of these reacts with this to form water, this shifts forward. So what you're going to see is that you're going to increase the solubility. If I lower the pH, I'm going to increase the solubility. So if I had magnesium hydroxide in solution, and I wanted to increase the solubility of that magnesium hydroxide, I'm going to have it in a solution that has a low pH. And then I'm going to see more of this is going to be able to be solvated. So pH is going to have an effect, and it's going to depend. It's going to depend on the ions that you have in solution. So let's compare some ionic compounds. Iron carbonate, and this has a KSP of 3.07 times 10 to the minus 11. Let's compare magnesium hydroxide, which we just did, and let's compare calcium hydroxide. So here's a table of all of these, some selected solubility product constants. And what you see here is that a lot of them are really small. So these are all things that if we normally applied our solubility rules to, we would say they were insoluble. But what I see here is that there's going to be a small amount of ions that are going to go into solution, and I'm going to be able to find that by taking these KSP values, plugging those into the mass action. So if I want to look at three, I'm going to compare iron carbonate, this guy here, magnesium hydroxide here, and calcium hydroxide, and I want to see which one has the higher solubility. Can I just compare my KSP values? I can if I'm looking at calcium hydroxide and magnesium hydroxide. If I'm going to compare solubility, it's going to produce the most amount of ions in solution if my stoichiometry is the same in terms of number of ions. So this is going to dissociate to give me 3 ions. This is going to dissociate to give me 3 ions. So if my number of ions that are going to be produced between my 2 ionic compounds are the same, then I can compare my KSP values. So if I just look at these two here, and then I'll come back to iron carbonate. If I compare my KSP values, I'm going to assume that this is going to be more soluble because my KSP value is 10 to the minus 13 compared to 10 to the minus 6. So between these two, calcium hydroxide, there's going to be more of these ions in water than there is going to be of magnesium hydroxide. If I want to compare iron carbonate to these three, iron carbonate is going to dissolve into 2 ions where this is going to be 3 and this is going to be 3. So if I want to compare all 3 of these, I'm going to have to do something where I'm going to have to find S for all 3 of them rather than my KSP. Here I can compare my KSPs because these have the same stoichiometry, 3 and 3, but now I have 2 here. If I calculate my S just like I did here, for calcium hydroxide and iron carbonate, what I'm going to find are these values here. This S, which we've already calculated, this S here is going to be 1.05 times 10 to the minus 2, and this is a smaller value, so that also tells me that this is going to be more soluble. But what is my S here? My S here is 5.5 times 10 to the minus 6. So this is going to be the least soluble of all 3, even though its KSP is not as low as the KSP here. So in terms of soluble, this is still going to be the most soluble. So we've been looking at the solubility of these compounds just in pure water. What if I have a compound now where it's not just in pure water? So let's say I want to calculate my molar solubility of calcium fluoride in a solution with, so I don't just have pure water, now I have a solution that has something else. This is called the common ion effect, which means I'm going to see a change in my solubility more than what I would predict just based on my KSP. So let's look what's happening. If I have KF and I want to look at the solubility of calcium fluoride, if I just write that solubility, and my KSP is going to be equal to calcium and fluoride, and that's going to be squared, and I could look up this value. If I have a common ion effect, so I could look at this and say, okay, I can calculate my molar solubility just based on pure water. Let's just do that. We'll come back to what's happening up here. So let's just calculate S first. So remember, I don't care what's happening here with my solid because it doesn't go into my law of mass action. I'm going to assume that I have 0 here. My change is going to be that S. So I'm going to increase by S here. I'm going to increase by 2S here. So for every calcium ion, I'm going to also dissolve 2 fluorine ions. So this would be in pure water. But I don't have pure water. I have a solution that has 0.250 molar of calcium nitrate, and since one of these ions of my ionic compound I'm trying to solvate also has calcium, that's my common ion. So my common ion here is calcium because I have calcium up here. The nitrate's not going to do anything, but the calcium, now I can't start with 0 concentration of calcium because I have some calcium ions already in solution. And so if I have calcium ions already in solution, that's going to decrease my solubility. So I'm going to see my effect here, my change in solubility is I'm going to see a decrease if I have a common ion effect. A decrease, so my molar solubility is going to be even smaller than this. Let's do this calculation. I said I'm not going to do too many calculations with you today, but a few of them. This is 0, but this is 0.250 molar because that's how much calcium nitrate I have in solution. This is a highly soluble compound. So I'm looking at calcium, so my initial starting concentration is not 0, it's going to be 2.25 molar. I'm going to add S to that. This is 2S, this is 2S, and this is 0.250 plus S. Now, I can do something here where if my KSP is really small, which it is, and this is fairly high in concentration, so I'm looking at that 10 to the third difference again, then I can do my S is small approximation and get rid of it here. Because even if I add to this, this is so much higher than whatever I would have that I would be adding. It's really not going to change this amount appreciably. So instead of my X is small approximation, this is my S is small approximation. And instead of removing it from a reactant, I'm removing it from a product. So a little bit of a different scenario here. That makes my math a lot easier. Now when I calculate my molar solubility, what you see here is that it has reduced, it's gone down. So in pure water, this would be my molar solubility. This is my molar solubility in 0.250 molar calcium nitrate, because these calcium ions that are in that solution are really effectively shifting the equilibrium back to the undissociated ionic compound here. So common ion effect. You're looking for, does the solution that you have you're adding your ionic compound to dissolve in, does it have an ion in common with what you're trying to dissolve? If it does, it's always going to decrease your solubility. Here, and then we're going to resume with the rest of this part in part 3B.